Dear learners, greetings from IIT Guwahati. We are now in the MOOCs course Fundamentals of Compressible Flow, Module 6, that is Supersonic Nozzles and Diffusers. So, in this particular lecture, I will discuss mainly on isentropic nozzle flow. So, prior to this module, we have discussed about some of the important aspects of shocks and expansion waves, and I will give a brief overview what we have been studied, and subsequently we will be discussing that how these concepts can be used for practical applications and in particular nozzles and diffusers. The other important aspect is that before you go to nozzles and diffusers, first thing we have to know that how we can establish a isentropic flow in the nozzles and diffusers. In fact, that is treated as a thermodynamic benchmark based on which the efficiency or performance of nozzles and diffuser will be evaluated. So, on these aspects, first we will talk about isentropic flow through a variable area duct, that means that is the first basic fundamentals. Subsequently, we will say that how this variable area duct can be useful for generating supersonic nozzle flow or subsonic nozzle flow, and all these supersonic and subsonic nozzle flows, first thing that benchmark that we are going to discuss about isentropic flow in the nozzle. So, this is the complete overall picture for these lectures, and towards the end of the lecture we will try to solve some of the numerical problems. So, before I go to the nozzles and diffusers part or isentropic flow in the nozzle, let me recall that what are the topics that we have been covered. First thing, shocks and expansion waves. In the shocks category we have a normal shock and we have oblique shocks, and the beginning of shock wave formation starts with a Mach wave, followed by this Mach wave becomes an oblique shocks with a when this shock angle increases, and in particular this oblique shock is formed when the supersonic flow encounters a concave kernel. Now, when the shock wave becomes stronger and stronger, this oblique shock becomes a normal shock, and in contrast when the supersonic flow encounters a convex kernel, it tries to bend, and this expands, and when the flow tries to bend, it has to pass through infinite number of expansion waves through certain turning angle, and this expansion flow process is entirely governed through the Frankel-Mayer expansions. And with respect to shock point of view, we have discussed about theta beta m relations, based on which we can have a attached shock or detached shock wave, and this attached shock and detached shocks can be formed depending on the angle or the flow deflection angle, and if the flow deflection angle is less than the maximum value as assigned by the theta beta m relation, then it becomes an attached shock, and in all other situations you will have a detached shock, and this detached shock normally we call as a curved shock or bow shocks. And in a particular application, when a supersonic aircraft is flying at very high velocity, then what may happen is that there may be a continuous oscillations of these oblique shocks, and this oblique shock will be either it will be a curved shock or it will be a bow shock, and it tries to oscillate in the front part or of the nose portion of this aircraft. And this particular phenomena is many times we call this as the aircraft is engulfed in a shock waves. Apart from this, whatever I have told, these are the some of the highlights. We have Frankel-Mayer expansion, we have oblique shocks, we have, and also we have discussed on the supersonic flow past wedge and cone. We have supersonic flow over blunt bodies, and based on this we have shock expansion theory, and there are many other practical or graphical representation of oblique shocks like shock polar, pressure deflection diagram, and some of the natural occurring situations, regular reflections, intersections of oblique shocks, MAC reflections. We have also introduced the solid boundary, free boundary, concept of slip lines, and all these concepts are now going to be utilized where when you discussed about nozzles and diffusers. And in some situations nozzles there will be formation of normal shock wave, there may be for situations of having oblique shocks or expansion waves depending on the flow phenomena that is happening in nozzles and diffusers. And all these understandings is very vital. So, let me start with the nozzle flow, and that is isentropic nozzle flow, but before I start that let me give you some background, that means how that isentropic nozzle flow comes into picture. So, prior to this lecture in one of the module we have discussed quasi one dimensional flow through a variable area duct. So, when we have a variable area duct system, we have said that at a particular location the area changes with the x direction, and this particular concept has been further extended to make it useful whether we can use the concept for a nozzle or diffuser. Now, where we find this nozzle and diffusers, and typical application we have is the aircraft or rocket engines. In fact, nozzle is the basic essential component of aircraft and rocket engine because it is the main source of thrust generation. And in addition to this, this is how we do it in the engines. There are some wind tunnel facilities, and in particular supersonic wind tunnels, where we want to simulate high altitude flight conditions in the laboratory. So, while using this in the laboratory, these nozzles and diffusers are the integral part of this experimental setups. So, these are the very basic components of supersonic flow, for which, because without nozzle we cannot generate a supersonic flow. And of course, we also require the opposite action of the nozzle. So, you have need a diffuser because you have to release the flow to the atmosphere. Now, while releasing the flow, we must have the flow velocity which is getting exhausted should have very minimal value or close to stagnant value, such that we will have minimum pressure loss. So, these are the fundamental aspects that why we require nozzles and diffusers. So, let me start with the very basic things that when you deal with isentropic flow in a variable area duct, and typically we call this as a convergent divergent passage, and these things we have studied through quasi one dimensional approach. So, there we have mentioned or we have found that it is possible to accelerate or decelerate a supersonic flow through a convergent divergent passage by maintaining appropriate pressure difference upstream and the downstreams. Now, this convergent divergent passage can be called as a nozzle, either it can be called as a nozzle or diffuser. So, if this convergent passage has to perform a nozzle actions, the flow is accelerated with drop in pressure, and this convergent passage, if it is used for a diffuser action, then it decelerates the flow with increase in the pressure. And these fundamental concepts is one of the important consequence that of a geometrical passage that can be used as an experimental tool or device which can accelerate or decelerate the flow in a compressible medium. And in a generic convergent divergent passage, we have seen there is a minimum area, because that is the minimum area, one particular location the area will be a minimum, and that thing we call this as a throat. That means minimum area location we call this as a throat. And the characteristics feature of this throat is that, or this location is that, irrespective of what action it performs, either nozzle or diffuser, flow is always sonic. That means, if you have keeping a required pressure difference, we can have, there will be a sonic flow only at the throat. And we can do the quantitative analysis through quasi dimensional approach, by which we can find out the flow Mach number depending on the upstream and downstream pressure and temperature differences. Now, if you look at a particular figure which is a convergent divergent passage, in one case it is used as a nozzle action and in other case it is used as a diffuser action. What happens with very basic philosophy, if you have inlet flow is subsonic, now this subsonic flow when it sees a converging passage, its velocity increases and it becomes sonic at the throat, that means at the minimum area. And when it becomes sonic and this particular at this location, the supersonic flow again sees a diverging passage. So, it further expands, that means in a continuous converging diverging passage the flow velocity continuously increasing at the cost of pressure drop, at the cost of decrease in the pressure. So, this particular, since the velocity is continuously increasing, so we call this as a nozzle action. So, this acts as a nozzle. But in contrast, if you have a, instead of subsonic flow, if you want to, we have a supersonic flow inlet and you want to continuously decelerate the flow, then first the unit enters. So, the flow becomes sonic and at this sonic point it says a further diverging passage. Now, if you do not put adequate pressure difference, then the velocity will continuously decreasing. So, in a sense that a supersonic flow can be decelerated to a subsonic value through a converging diverging passage. So, this is the very basic philosophy of variable area duct concept in a isentropic flow. Now, this in our earlier analysis, when you deal with quasi one dimensional approach, there we derived many important relations and we also mentioned that the complete flow is isentropic in nature. So, the isentropic relation between the static temperature and stagnation temperature ratio, that we call this as stagnation to static temperature ratio, stagnation to static pressure ratio, stagnation density to static density ratio. So, all of them are function of Mach number. And if you want to use these particular relations with respect to Mach 1, that is which is at the throat locations, we get a very simplified relations and at Mach 1 this becomes a characteristics number, that means T star. So, this static value becomes the characteristics temperature because it corresponds to Mach 1 and characteristics pressure and characteristics density, and these ratios are nothing but the fixed numbers. And for gamma is equal to 1.4 AR, this static to stagnation temperature ratio becomes 0.833, static to stagnation pressure ratio becomes 0.528 and static to stagnation density ratio becomes 0.634. So, this particular relations is maintains always maintained. So, a very basic philosophy for this is that if you want to accelerate or decelerate a flow, then we must know that why the sonic flow happens at the throat, because this particular and this particular sonic condition is possible only when these pressure ratios are taken into account. So, this is one aspect of when the flow is controlled through pressure and temperature or density. But now there is with respect to this area change, the flow is also governed with as a function of Mach number. So, this relation we call as a area Mach number relations. So, the area Mach number relation, if you look at that, this area, that means area ratio, we call this as, typically we call this as area ratio A by A star. So, A is the any area at any arbitrary locations and A star it refers to at the throat. So, this location we say star throat and at this location we say A star and or any other locations either you can say A. So, based on this area Mach number relation is framed, and if you look at this area Mach number relations, it is a quadratic in nature and it has two solutions. One is supersonic value, other is the subsonic value. That means, for a given area ratio there are two possible values of Mach number, one is of subsonic value, other is the supersonic value. That means, for a given area ratio we can get a subsonic Mach number or supersonic Mach number. This is one aspect. Another important aspect is what we are looking at, when the flow is choked, we call this as a choked mass flow rate. When I say choked mass flow rate, that is that mass flow rate is normally defined as rho u times A. So, density multiplied by velocity multiplied by area, and this, in this case the area is nothing but the minimum area. So, if you take the value of rho star from this equation, u star is nothing but A star. So, A star and u star they are same, and that is u star we can write in form of A star, and this A star is nothing but square root of gamma r T star, and this T star will come from this particular relations. And when you put all these things here and A star from here, we can calculate the mass flow rate. And it is interesting to see that when you calculate the choked mass flow rate, it is governed with three main important factor. One is the geometric factor A star, which is nothing but the minimum area location. Other is P naught and T naught. P naught and T naught are nothing but the reservoir conditions. So, reservoir condition is nothing but your upstream conditions. So, where the flow actually enters. So, at that conditions we say the stagnation pressures and temperatures are P naught and T naught. So, and these are we call as reservoir condition. So, choked mass flow rate is now a fixed number, and it has nothing to do with any other location except at the throat. Okay. Now, let me start the first concept, that how a isentropic supersonic flow is established and why we say it is a nozzle action. So, consider a convergent divergent nozzle for which area ratio is very large, in which air enters from a reservoir. So, the first figure shows here that we have a converging diverging passage and the area ratio is very large, that means your inlet to this throat seems to be very large number, and the reservoir conditions are P naught and T naught, and it tries to enter. And when it tries to enter, that means when a flow has to enter into it, when there must be adequate pressure difference, and we are maintaining a pressure exit pressure P e, so that we can have a adequate flow that flow into this nozzle. And here we are looking at a solutions that flow in the nozzle should be a supersonic flow. So, when it tries to enter, since these pressures are too very high, so the flow tries to rush to this converging passage. So, when it tries to rush, that means when it is at reservoir conditions, its flow is almost 0 velocity, and when it tries to rush, it accelerates. So, at one point at the minimum area, the flow becomes sonic, and the sonic flow sees a diverging passage, and also it sees adequate pressure difference, so it further accelerates. So, in a continuous way we can get a supersonic flow in the at the exit of this nozzle. And if you try to put, if you recall our area Mach number relations, this particular area Mach number relations we can frame. So, here x stands for the location at which area is calculated. So, x stands for the A, that means the location at which this area is calculated, and this particular follows a particular fashions. And if you look at this Mach number versus x plot, and you will see that initially the flow tries to the Mach number continuously increases till sonic, again it further increases, and finally this based on this area the Mach number is fixed at this particular locations. So, a fixed value of Mach number, we call this as the exit Mach number, ME, is achieved at the exit of this nozzle. Now, corresponding to this Mach number, we also can have a pressure ratio relations, that is exit pressure can be exit pressure to stagnation pressure ratio is also a function of Mach number. And similarly, for temperatures also we can have temperature Mach number relations. So, in this process the pressure and temperature continuously falls, and as you can see that when the area is at the sonic, the flow is sonic at the throat, that is Mach number at 1, at that point of time the pressure ratio P by P naught becomes 0.528, which we have established in our earlier calculations, and similarly for temperature ratio T by T star becomes 0.833. So, these numbers are very fixed numbers for any situations. So, this is entire philosophy that how a supersonic flow is established in the nozzle, and entire analysis of this nozzle flow, that we do not, the two things that we must remember for the supersonic nozzle flow. First thing, adequate pressure ratio has to be maintained. Second thing, the Mach number is governed by two factors, one is area ratio, other is the maintaining pressure ratio. So, this is how the supersonic flow is established in a nozzle. And another important aspect of the supersonic nozzle flow, and since we are talking about isentropic flow, so and that means entropy do not change. So, it is a complete shock free environment. So, it is for a complete shock free environment, that means we can use these isentropic relations, and Mach number is always supersonic at the exit, and the minimum pressure value is fixed through the isentropic relations. That means, for a given nozzle, if you maintain this particular ratio by following this equation, for example, if you want a Mach 6 nozzle, then if you put Mach number here, then you will get P by P naught value, and that is the minimum pressure that you must keep. And if you put below this value, the flow will be supersonic. If you keep any value above this, the flow will not be supersonic. So, this is the very basic philosophy, and we can see that for an isentropic case, if it has to be isentropic nozzle, there is only one possible solutions of supersonic flow at the exit. So, this is the most important aspect, that there is only one solution for nozzle flow when in a isentropic case. So, this is how we talked about isentropic supersonic flow in the nozzle. Now, let me discuss about isentropic subsonic flow in the nozzle. Now, you recall this our earlier analysis, that when you talk about isentropic subsonic supersonic flow, we have established the isentropic relations, and once we follow those isentropic relations, we can easily say that we can establish a supersonic nozzle flow. Now, let us see another situation where we want to establish a subsonic flow. So, for a normally this is not a routine practice when you talk about a flow in a convergent divergent passage, and that too for a subsonic nozzle. So, this is not a conventional practice, but this can be treated as a starting situation. That means, when a nozzle is started, so it has to start from a subsonic solutions, and finally will land off this supersonic value. For example, if you want to maintain this area Mach number, pressure ratio, temperature ratio, whatever we established, all of a sudden we cannot achieve these ratios. So, this has to start from a base value or some beginning value, and will slowly it go to a supersonic number, and when you reach that supersonic number, it becomes a unique. To start this nozzle, we have to start with the isentropic subsonic nozzle flow. So, it has to start from the subsonic value, and finally it approaches the supersonic value. So, this starting phase is now established in a similar philosophy. So, for the starting phase, we are trying to say that just like that, if you keep a nozzle on a table, the flow is not going to happen. When for the flow to have happened, we have to create an adequate pressure difference. So, that way we call this as exit pressure is introduced, which is controlled in the downstream of the nozzle through some independent mechanism, and this upstream pressure is still may be a reservoir pressure. So, what we can say is that So, instead of putting one particular exit pressure, we will put that there is some pressure we are maintaining, we call it as a PE, and this P naught and T naught still we can say it is a reservoir condition. So, basically this convergent divergent passage is connected to a reservoir which has a very large value of a inlet to throat ratio, or A by A star is very. So, here we will not say that it is A star, we will say it is a throat. And another point that I need to emphasize, that when you say it is a supersonic number, so we said the throat is the minimum area, and at this minimum area sonic flow happens. But when we say subsonic flow, throat is also a minimum area, but not necessarily the flow will be sonic. So, this is the very basic philosophy, that how whether AT throat is approaches to A star or not. So, this throat is approaches to A star when it is supersonic, and AT and AT becomes the again this minimum area when the flow is only subsonic. So, these things we have to fundamentally make it very clear from the beginning. So, so if this particular converging passage, if you look at here, so we have a minimum area which is called throat, and this reservoir condition are P naught and T naught, and exit condition is the exit area is AE and its pressure is PE. So, if ideally if PE is equal to P naught, there will not be no flow. Now, if PE is slightly less than P naught, then there will be some flow that is going to encounter. Now, if PE is slightly below that, that means initially PE value starts with PE1, there is some flow is going to happen, then it further reduces, becomes PE2, the flow again accelerates, and PE3 for the it reduces further, the flow further accelerates. So, in this way that we can get the continuous air to get accelerated in this converging diverging passage. Now, let us see how when this happens, this happens, how you look into the pressure temperature ratios. So, here this particular figure talks about this whatever I have discussed, that when during the start of the nozzle flow, this exit pressure and P naught they are almost same. So, in the beginning we start a first value of pressure ratio, that means we give a very marginal pressure difference. So, that ratio becomes PE1 by P naught. Okay. And when you have this, there is some flow that enters into this passage, and by looking at the area Mach number relations, it follows this particular path. If you look at this particular things, the Mach number increases, and at the minimum area Mach number continuously increases, because this flow is subsonic, the Mach number continuously increases, but interestingly it is not sonic, and it increases, and when it sees here it does not see a sufficient pressure ratio. So, the flow cannot accelerate further. So, the Mach number drops. So, this is how it happens, because it is here it sees that there is no adequate pressure ratio, and the sonic flow when doesn't see the adequate pressure ratio, it tries to its Mach number, the flow Mach number continuously drops in the diverging passage. And this also keeps on happening all possible values of this Mach number ME1, ME2, and one particular instant at ME3, what happens? That means we are at that particular instant we have maintained a substantial high value of pressure differences. So, because of this reason the Mach number increases to a sonic value, but when it sees a sonic value and and the flow again drops here, because flow again drops here because this Pe3 is not the value at which your isentropic relations has been established. So, this Pe value does not fall into this. That means, even though the flow is sonic, but still it does not see the required pressure ratio which is supposed to be there when we need to have a supersonic flow. So, again this, even though the flow is sonic, pressure ratio is not sufficient. So, the flow further the Mach number further drops in the diverging section. So, this is how the characteristic feature of the subsonic flow. So, in this way we have just given only 3 possible solutions. So, in this category there could be infinite number of solutions, like we have Me1, Me2, Me3, Me4, like Me, all these things there will be possible solutions. So, that means a subsonic flow has infinite number of solutions. The other important features what I can say is that the decrease in the exit pressure will accelerate the gas in the converging portion. So, the variation of local Mach number and static will be larger. That means, at one particular instant the exit pressure is such that flow is sonic at the throat and the area ratio Mach number can be applied. At that location area Mach number relation can be applied. But this exit pressure is not sufficient to expand the sonic flow further. So, again the Mach number drops. So, in a subsonic flow that we can have infinite solutions, but there is one particular pressure at which the flow can be sonic, but it will not expand further in the diverging passage. And because of this reason, the characteristics features of pressure ratio now becomes this way. That means, beginning you have pressure ratio Pe1, and slowly when you have pressure ratio Pe3, so this pressure ratio is slightly less. And finally, we will also talk about the choked mass flow rate conditions. We will use the same relation here, and this particular picture shows that how the mass flow rate varies with the exit pressure. So, if you see the exit pressure Pe, and when there is no mass flow, the exit pressure was P naught. When there is no mass flow, that means the nozzle has not started, and slowly when you reduce this pressure, maybe Pe1, another value is maybe Pe2. So, as a result the mass flow rate continuously increases in this fashion, and one particular value Pe3, and that Pe3 nothing but 0.528 P0. At that point we say the Mach number is sonic at throat. That means AT becomes A star. So, Mach number becomes sonic at the throat. So, that particular instant your pressure ratio, that means Pe3 becomes 0.528 P naught. When this is maintained, then the mass flow rate becomes choked. That means, mass flow rate has a fixed value. Whatever value of pressure ratio you maintain in the downstream, the mass flow rate becomes a fixed value. So, this fixed value is defined by this particular number, m star is equal to P naught A star square root by T naught, and entire multiplied by this particular number, that is square root of gamma by r multiplied by twice by gamma plus 1 whole to the power gamma plus 1 by gamma minus 1. Now, if I summarize the entire philosophy, I will say that we have discussed about isentropic flow through nozzle. One is the subsonic nozzle flow, other is the supersonic nozzle flow. This complete picture is represented here. Now, when the nozzle is initially started, we started with a very low value of pressure at the exit, Pe is equal to Pe1, and there we have a very marginal change in the Mach number, as if there is Mach number variation is very less, and if you keep on increasing the pressure ratio P1 to P2, Mach number further increases from Me1 to Me2, and at the flow is subsonic, flow is sonic at the throat at one particular value of Mach number Me3, flow is sonic at the throat, at the same time the flow is not supersonic at the exit, and the exit Mach number is also subsonic. In that case also the value is Me3 and corresponding pressure ratio is Pe3 by P0. So, this is what the subsonic solutions. Now, when this Pe3 becomes a fixed value, that means, if Pe3 corresponds to this value, if I maintain this Pe3 to a value which corresponds to the isentropic value, that is P by P0 is equal to 1 plus gamma minus 1 by 2 m square to the power minus gamma by gamma minus 1. That means, one particular instant this exit pressure is Pe, and this at this exit pressure we have a Mach number Me that is fixed, and that Mach number is first fixed by this area ratio, and also it is fixed by when the area ratio is satisfied and the pressure ratio is also has to be satisfied. At that location we will have only one particular solutions we call this as a supersonic nozzle flow, and at that situations we will have a fixed number, that is P by P0 will be 0.528, T by T0 will be 0.833. So, here if you see there is only one curve, but here you can see there are many curves. So, we say that a subsonic flow will have infinite number of solutions and a supersonic flow nozzle flow will have only one solutions. So, this is how I have summarized the isentropic flow through nozzle. The subsonic flow in a convergent divergent nozzle is entirely governed by the pressure ratio between exit and the inlet of the passage. In the event of non-adequate pressure ratio, the flow is mostly subsonic and there are infinite number of isentropic solutions. The flow need not be sonic at the throat even if it encounters the minimum area of the passage. The mass flow rate through the nozzle will increase if the exit pressure decreases. So, it can be calculated by using the continuity equations. When the exit pressure ratio is maintained or exit pressure difference is maintained, the final Mach number is fixed by the area ratio between the exit and the throat of the nozzle. So, this is the only one possible solutions for a supersonic flow at the exit. So, in the supersonic solutions, the mass flow rate through nozzle is also fixed by the choke flow condition at the throat. Okay. So, this is all about the isentropic nozzle flow, and it is characterized as a shock free, and we have a supersonic nozzle, we can have a subsonic flow in the nozzle. So, with this we come to the end of this lecture, and now I will try to solve some numerical problems based on the isentropic flow in the nozzle. So, the first problem that is given to us, that we have a subsonic and supersonic flow through a convergent divergent nozzle for which the reservoir pressure and temperatures are given as 9 bar and 290 Kelvin. So, we have to calculate the Mach number, pressure, temperature, flow velocity at the location where the exit to throat ratio is 6. So, let us first draw the schematic of the problem. So, the schematic, which is nothing but we have to draw the a convergent divergent passage which is supposed to look like a nozzle. So, we have two locations, basically we have three locations. We have one is inlet, throat, other is exit. So, initial conditions in the reservoir we have given as P0 is equal to 9 bar, T0 is equal to 290 Kelvin. Okay, this condition is given, and we are given with A exit through throat area, that means AE by A star is equal to 6. Determine the flow velocity at locations where exit through throat area is 6. So, that means there are two locations for which we have to calculate the area ratio A by A star is equal to 6. So, to solve this problem, first thing that we have to recall is that we have to see that area Mach number relations, which is a function of area ratio is a function of Mach number. And if you look at this particular equation, it is to solve the equation, if you know the Mach number, it is easy to find the area ratio, but at the same time if you have area ratio given, getting Mach number will be a difficult task. So, for that case we have this isentropic solution chart table, where it is represented the area ratio is represented at the Mach number, and side by side we have static pressure, stagnation pressure ratio, stagnation pressure density, stagnation density ratio, and stagnation temperature ratio as well. So, it is easy to use this table when you deal with this kind of problem. So, to solve the problem, first thing that we want to have, for this area ratio A by A star 6, we can have two solutions, one is subsonic, other is supersonic. So, let me start with first what is the subsonic solution. So, for subsonic solutions, for this area ratio 6, we can look for a value in the subsonic range. So, area ratio 6 may be somewhere in this location, we will have area ratio close to 6, and that number is slightly below the value of close to the value of 0.1, and that number at 0.1 this value is 5.82. So, I can still choose a value slightly less than that. So, maybe approximate Mach number would be 0.097. If the for 5.82 this close Mach number is 0.1, and for 6 ratio this number can be approximated as this. Now, when you have this thing, we have this P naught by P ratio, we can calculate 1 plus gamma minus 1 by 2 m square to the power gamma by gamma minus 1, and we know this m, so P naught by P can be calculated as 1.006. Similarly, T naught by T, we can say 1 plus gamma minus 1 by 2 m square, and this value would be close to 1.004, and from this we can say we know P. So, we can say P value will be 8.94 bar, and T value can be close to 288 Kelvin, because this P naught and P value are almost same and the flow is close to it is a subsonic solutions. And to what we also require, calculate the, we got Mach number, we got pressure, temperature, now you have to find the flow velocity. So, flow velocity U is nothing but mass m Mach number into A. So, A is nothing but speed of sound, Mach number is known. So, m into square root of gamma r T. So, temperature is known, gamma for air 1.4, r is 287. So, we say U can be calculated as 0.097 square root of 1.4, r is 287 into T is 288. So, this will say U will be about 33 meter per second. So, this is how we obtain a subsonic solutions. Then for supersonic solution, we will use this number, that means A by A star 6 will give you the Mach number close to this number for 0.59, 5.9, this number is close to 3.35. So, we can say approximately Mach number is 3.35. So, in that way we can calculate P naught by P would be 61.5, we can get it from here, and T naught by T is 3.244. So, from this we can say P is P can be calculated as 0.146 bar, because P naught is 9 bar, T naught is 290 Kelvin, and temperature would be 89.5 Kelvin. Then we got pressure, temperature, we require flow velocity. So, A becomes square root of gamma RT. So, the speed of sound will be 189.6 meter per second. When A is given, so you can say U is equal to M times A. So, M is 3.35, it is A is 189.6. So, U becomes 635 meter per second. So, this is how we say the problem solved is for this area ratio 6. Now, the question, next question, part of this question, if the throat area is 0.4 meter square, calculate the choked mass flow rate. So, choked mass flow rate, that can be calculated, mass flow rate choke. So, when you say choked flow rate and that the choked condition, we can say A star would be square root of gamma R T star, and M is equal to rho star A star U star. So, A star is given as 0.4 meter square, okay, and the rho star by rho naught, already you have this ratio 0.634, and T star by T naught is 0.833. So, these relations are there for when the mass flow is sonic at the throat. So, from this we can get rho star as 6.94 kg per meter cube, because rho naught we can find out P naught by R T naught. So, P naught is 9 bar, 9 into 101,325 R 287 into T naught is 290. So, rho naught would be 10.95 kg per meter cube. So, when you have rho naught, we can find out rho star. Then T star, T naught is given 290, so T star would be 241.57. So, T star is known to us. So, you can say U star. U star is nothing but A star, that is square root of gamma R T star. So, when you put this U star would be 311.5 meter per second. So, when you put all this number, then M star mass flow rate can be calculated as 868 kg per second. So, this is the choked mass flow rate. Now, second part is that where the exit to throat area ratio is 6. So, when you have exit to throat area ratio, So, at that location when you have a subsonic value or subsonic solution, we have u is equal to 33 meter per second. That point your density is equal to P by RT, that can be calculated as 10.95, because at the subsonic flow density is close to stagnation density. So, the kg per meter cube, and rho A is 0.4 meter square. So, when you put this, multiply this, we can get mass flow rate as, instead of this m, we can say is m would be close to 868 kg per second. And similarly for the supersonic flow, we also know u, a and a, and so supersonic value, this choked mass flow rate also will be of same number. So, it means that the choked mass flow rate, whether you calculate the based on the value based on the at the location, or we calculate the value rho star, a star, u star. So, its value is always fixed, that is 868 kg per second. The second problem is another interesting problem, where air enters in a converging diverging passage with exit to throat area ratio 2, reservoir pressure is 2 bar and exit pressure is 1.9 bar. So, again we have same relation A by A star as a function of Mach number, and for that what is given, A E by A T is given as 2. So, for this 2 we can get close to, first thing let us see if you have a supersonic solution. So, if you have a supersonic solution, so A be close to 2, this number could be in this line. So, it is 2.005. For that we can say Mach number is close to 2.2. So, ME can be considered as a supersonic value 2.2, and if you say this, P naught by P would be PE 1 plus gamma minus 1 by 2 ME square to the power gamma by gamma minus 1. So, this number would be 10.69, which is here. Now, if this is the case, your exit pressure should be P naught by 10.69. So, your number is 2 bar. So, 2 by 10.69. So, this ratio will be 0.18 bar. So, actually to have supersonic flow, we must have exit pressure 0.18 bar, but that is not maintained here, where your exit pressure is 1.9 bar. So, this will say is no supersonic solution. Is possible for this particular situations. So, we will have a subsonic solution. So, we must see that subsonic value, but in that subsonic solution not necessarily that flow will be sonic at the throat. So, for which we have to first find out what is the actual ratio. So, P naught by P E in the actual case would be 2 by 1.9. So, 2 by 1.9 becomes 1.053. When the pressure ratio is 1.053 and 1.053 ratio, when if you look at this particular table 1.056, for which the subsonic value of Mach number ME has to be 0.28. So, here exit Mach number is 0.28 actually. So, we do not have supersonic solution. So, exit Mach number is this. This first part is got answered. You have Mach number at the exit is 0.28, but we also require what is the Mach number at the throat. Flow is not sonic, so you have to calculate the Mach number at the throat. So, for that we have to find out AT, this particular area ratio, that is AT by A star. So, AT by A star can be written as AT by AE into AE by A star, and for this 0.028 this can be 2.17. So, this will give you AT by AE would be 2.166. So, this will be 2.166 into, actually exit to area ratio is 2. So, this would be 1.085, and for this 1.085 area ratio, if you actually look at the Mach number value, so 1.08. So, this refers to the Mach number 0.72. So, M star would be 0.72. So, for this situation your Mach number is not sonic, it is only the value of 0.72. So, this is how you have to attack the problem considering the area ratio as well as the pressure ratio situations simultaneously. Even third is another similar problem which is simple. So, for a convergent divergent duct, exit to thread ratio is 1.6. So, AE by A star, if it is 6, and here you have to find out to achieve the sonic flow. So, that means M is equal to 1. So, AE by, instead of throat I have written here A star, because we say we have to achieve a sonic flow. So, for this area ratio solution, when you have 1.6, then for this area ratio of 1.6, we can say, we can record here about the Mach number. So, 1.59 we have found out this close to this number. So, 1.59. So, Mach number at the exit. So, this will refer Mach number at the exit is close to 0.4, and for this Mach number this says that P naught by PE exit pressure is 1.117. But what is the question that is asked? What value of exit to reservoir ratio? So, we want the reverse. So, PE by P naught would be 1 by 1.117. So, this is 0.895. So, exit to reservoir pressure ratio will be 0.895. Okay. So, this is how the problem is very simple, as long as you are going to use this isentropic table for area Mach number relations, and side by side we must also look into that what pressure ratio is maintained between the reservoir and the exit. So, based on that decision has to be taken whether you have to go for a subsonic or supersonic solutions. So, with this I conclude this lecture for today. Thank you for your attention.